In the vast darkness of space, far beyond the familiar glow of our own sun, there exist worlds so strange and distant that they challenge everything we thought we knew about planets. These are not the invented fantasies of science fiction, but real places discovered by humanity's most sophisticated instruments. The Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, known as TESS. Together, these observatories have unveiled a cosmic menagerie of planets that orbit distant stars, each one a genuine world with its own unique characteristics. Let's begin our journey quietly, gently, as we drift through the concept of how we find these worlds. Imagine standing in a meadow on a clear night, looking up at the stars. Each pinprick of light you see is a sun, potentially accompanied by its own family of planets. For most of human history, we could only wonder if such worlds existed. But in 1995, the first exoplanet orbiting a sun-like star was confirmed, and since then, our understanding has blossomed like flowers opening to the morning light. The Kepler Space Telescope launched in March 2009, carrying with it humanity's hopes of answering an ancient question: are we alone in the universe? Named after the German astronomer Johannes Kepler, who discovered the laws of planetary motion in the 17th century, this observatory was designed with a singular, beautiful purpose: to stare at a single patch of sky, watching approximately 150,000 stars simultaneously, looking for the telltale dimming that occurs when a planet passes in front of its star. This method, called the transit method, is elegantly simple in concept. When a planet crosses between us and its star, it blocks a tiny fraction of the star's light, sometimes less than 1%. By measuring this dimming with extraordinary precision, scientists can detect the presence of a planet millions or even billions of miles away. The amount of light blocked tells us the planet's size. The time between transits reveals its orbital period. And from these two pieces of information, combined with knowledge of the star itself, we can begin to understand what kind of world we have found. Kepler operated for 4 years in its primary mission, from 2009 to 2013, before mechanical failure affected its pointing ability. But even after this setback, engineers devised a clever solution, and Kepler continued observing in what became known as the K2 mission, using the pressure of sunlight itself to help stabilize the spacecraft. By the time Kepler's fuel was finally exhausted in October 2018, it had discovered over 2,700 confirmed exoplanets and identified thousands more candidates awaiting verification. Then came TESS, launched in April 2018, designed to continue and expand upon Kepler's legacy. While Kepler focused on one distant region of sky, TESS surveys nearly the entire sky, dividing it into 26 sectors and observing each for approximately 27 days. TESS focuses on stars that are closer and brighter than those Kepler studied, making the planets it discovers easier targets for follow-up observations with other telescopes. Since beginning its mission, TESS has confirmed over 400 planets and identified thousands more potential worlds. Together, these two missions have transformed our understanding of planetary systems. Before Kepler, we knew of only a few hundred exoplanets. Now, we know of over 5,000 confirmed worlds, with many thousands more awaiting confirmation. We have learned that planets are common. Perhaps every star in our galaxy hosts at least one planet on average. We have discovered that planetary systems come in endless variety, that nature is far more creative in building worlds than we ever imagined. As we prepare to explore the strange planets found by these missions, let your mind settle into a state of peaceful curiosity. We are about to visit worlds where years last only hours, where metals rain from crimson skies, where multiple suns rise and set in alien patterns. These are not fantasies. They are real places discovered through careful observation and mathematical precision. Each world we will visit has been seen, measured, and cataloged. Each has a designation, a size, a mass, an orbit. Each is as real as the Earth beneath your feet, though separated from us by distances so vast that light itself takes years or decades to traverse them. Close your eyes for a moment and imagine the universe as it truly is, not empty, but filled with worlds beyond counting, each one unique, each one waiting to be understood. This is the gift that Kepler and TESS have given us. The knowledge that we live in a universe rich with planets, a cosmos where worlds are as common as grains of sand on an endless beach. And now, we will explore some of the strangest, most remarkable of these distant places, one gentle chapter at a time. Let us drift now toward a class of planets that were among the first exoplanets ever discovered, worlds so unexpected that they forced astronomers to rewrite their theories of how planetary systems form. These are the hot Jupiters, gas giant planets similar in size to our own Jupiter, but orbiting terrifyingly close to their parent stars. Imagine a world as massive as Jupiter, with its great swirling storms and bands of colored clouds, but placed not at a comfortable distance where water freezes, but instead positioned so close to its sun that its year, the time it takes to complete one orbit, lasts only a few Earth days, or sometimes just hours. The temperature on such worlds is not the frigid negative 200 degrees Fahrenheit of Jupiter, but instead reaches thousands of degrees, hot enough to vaporize metals. The first hot Jupiter discovered was 51 Pegasi b, found in 1995 orbiting a sun-like star approximately 50 light-years from Earth. This discovery was revolutionary, winning its discoverers the Nobel Prize in Physics in 2019. Before this finding, our only model for a planetary system was our own solar system, where small rocky planets orbit close to the sun and large gas giants orbit farther out. The existence of a Jupiter-sized planet orbiting closer to its star than Mercury does to our sun seemed impossible. Yet there it was, revealed through the subtle wobble its gravity induced in its parent star. Kepler and TESS have found hundreds of these hot Jupiters, each one a laboratory for understanding extreme planetary conditions. Consider KLT 9b, discovered by the Kilo-degree Extremely Little Telescope Transit Survey and confirmed through follow-up observations. This planet orbits a star 350 light-years away in the constellation Cygnus. It is tidally locked, meaning one side always faces its star, just as our moon always shows the same face to Earth. The dayside temperature of KLT 9b reaches approximately 7,800 degrees Fahrenheit, hotter than the surface of some small stars. At such temperatures, molecules break apart into individual atoms. Even hydrogen molecules split into atomic hydrogen. The planet is so hot that it is actually losing mass, its atmosphere streaming away into space like a comet's tail. Another remarkable hot Jupiter is WASP 12b, located roughly 1,400 light-years away. This planet is so close to its star that it completes an orbit in just slightly more than one Earth day. The intense gravity of its star is stretching the planet into an egg shape, and the planet is gradually spiraling inward, destined to be consumed by its star in approximately 3 million years, a brief moment in cosmic time. The dayside temperature exceeds 4,000 degrees Fahrenheit, and observations suggest that the planet absorbs nearly all light that hits it, making it darker than fresh asphalt. HD 189733b offers another window into these extreme worlds. Located 64 light-years away in the constellation Vulpecula, this planet has been studied extensively due to its favorable orientation and bright parent star. Scientists have been able to analyze the composition of its atmosphere, discovering that it contains silicate particles, essentially tiny grains of glass. The planet's winds, which reach speeds of over 5,000 miles per hour, whip these particles around the planet. It likely rains glass sideways on HD 189733b, the shards glinting in the blue light scattered by the planet's atmosphere. The question naturally arises, how did these hot Jupiters form? Gas giants require large amounts of hydrogen and helium, which can only accumulate where temperatures are cool enough for ice to form, providing solid surfaces for gas to condense upon. In our solar system, this happens beyond what we call the frost line, farther from the Sun than Mars. Hot Jupiters, however, orbit where temperatures are far too high for their formation. The answer appears to be migration. These planets formed farther from their stars, where conditions were favorable, and then gradually spiraled inward over millions of years. This migration can be driven by interactions with the disk of gas and dust for which the planetary system formed, or by gravitational interactions with other planets in the system. Some hot Jupiters may have been flung inward in close encounters with other massive planets, their orbits becoming highly elliptical before tidal forces from their stars circularized them into the tight orbits we observe today. Kepler 7b presents a slightly different face of hot Jupiters. Located approximately 3,000 light-years away, this planet is extraordinarily puffy. It has a mass only about half that of Jupiter, but is 50% larger in diameter, giving it a density similar to styrofoam. It orbits its star every 5 days, and observations have revealed that it has clouds in its atmosphere. These are not water clouds like those on Earth, but likely composed of silicates and other minerals that exist as vapors at such high temperatures. As you contemplate these worlds, let your mind rest on the strange beauty of their existence. These are planets where the concept of weather takes on entirely new meanings, where storms are powered by heat that would vaporize rock, where day and night exist in eternal imbalance. One hemisphere forever scorched while the other remains in relative coolness. They remind us that nature is endlessly inventive, creating worlds we never imagined, yet doing so through the same physical laws that govern our own planet. Drifting gently onward in our exploration, we come now to a class of planets that does not exist in our own solar system, yet appears to be among the most common types of planets in the galaxy. These are worlds intermediate in size between Earth and Neptune, occupying a range of masses and compositions that our own planetary system somehow skipped over. Astronomers call them super-Earths and mini-Neptunes, though these names can be somewhat misleading, for these planets may be unlike either Earth or Neptune in their actual nature. In our solar system, we have a clear gap in planetary sizes. Earth, the largest of the rocky planets, has a diameter of approximately 7,900 miles. Neptune, the smallest of the ice giants, measures about 30,000 miles across, nearly 4 times larger. There is nothing in between. Yet Kepler's observations revealed that this gap is not typical. In fact, planets with sizes between these extremes appear to be the most common planets in the galaxy, orbiting around 30 to 50% of Sun-like stars. Let us consider Kepler 452b, one of the most Earth-like planets discovered by the Kepler mission. This world orbits a star very similar to our Sun, though slightly older and brighter, at a distance of 1,400 light-years in the constellation Cygnus. Kepler 452b is approximately 60% larger in diameter than Earth, placing it firmly in the super-Earth category. Its year lasts 385 days, remarkably similar to our own year, and it orbits within its star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. We do not know if Kepler 452b is rocky like Earth, or if it has a thick atmosphere of hydrogen and helium like a mini-Neptune. This uncertainty reflects one of the great challenges in studying these intermediate-sized worlds. A planet that is 50% larger than Earth could be a rocky world with perhaps 5 times Earth's mass, or it could be a lower-density world with a substantial atmosphere of light gases. Without knowing the planet's mass, which requires different observation techniques than the transit method, we cannot be certain of its composition. The Kepler mission discovered that there appears to be a division around a radius of about 1.75 times Earth's radius. Planets smaller than this tend to be rocky, with compositions similar to Earth, made of iron, rock, and perhaps some water. Planets larger than this threshold tend to have substantial atmospheres of hydrogen and helium, becoming more Neptune-like in character. This boundary, sometimes called the radius gap or Fulton gap, after its discoverer Benjamin Fulton, tells us something fundamental about how planets form and evolve. Consider K2-18b, a super-Earth or mini-Neptune orbiting a red dwarf star 124 light-years away. This planet made headlines when scientists announced the detection of water vapor in its atmosphere, along with possible signs of clouds. K2-18b is roughly twice Earth's diameter and 8 times its mass, orbiting its star every 33 days. Its position within the habitable zone makes it an intriguing target for studying whether such worlds might support life, though its likely thick hydrogen atmosphere might make it very different from Earth. The TESS mission has continued this exploration with discoveries like TOI 270 system, located 73 light-years away. This system contains 3 planets transiting their star, 1 super-Earth and 2 mini-Neptunes. The innermost planet, TOI 270b, is merely slightly larger than Earth and likely rocky, while the outer 2 planets are approximately 2.4 and 2.9 times Earth's radius, placing them in the mini-Neptune category. The system provides a beautiful laboratory for understanding how these different types of planets can form in the same planetary system. Scientists believe that mini-Neptunes may come in several varieties. Some might have rocky cores surrounded by thick hydrogen-helium atmospheres, like miniature versions of Neptune. Others might be water worlds, planets with deep global oceans overlying rocky cores, their surfaces entirely covered by water hundreds of miles deep. Still others might have lost portions of their original atmospheres through a process called photoevaporation, where intense radiation from their parent stars gradually strips away the lighter gases, potentially transforming mini-Neptunes into super-Earths over billions of years. GJ9827d illustrates this process. This planet, located 97 light-years away, is approximately twice Earth's diameter and orbits its red dwarf star every 6.2 days. Observations suggest it is currently losing its atmosphere, with water vapor streaming away into space. Scientists believe we may be witnessing a mini-Neptune in the process of transformation into a super-Earth, a transition that occurs as the star's radiation boils away the planet's atmosphere over geological time. Let your thoughts settle now on the profound strangeness of these worlds. Imagine standing on a super-Earth with 5 times Earth's mass. Your weight would be dramatically greater, though how much greater would depend on the planet's radius. The sky might be thick with clouds of exotic composition. Or perhaps you're on a water world, an ocean planet where no land breaks the surface of a global sea that extends down through layers of increasing pressure, becoming so compressed in its depths that it forms exotic phases of ice despite temperatures hot enough to boil water on Earth. These planets represent possibilities our solar system never explored. They are reminders that nature experiments with every configuration allowed by physics, creating worlds in every available niche. As we drift peacefully through our exploration, we begin to understand that the universe is far richer, far more diverse in its planetary systems than we ever dreamed when we knew only the worlds of our own sun. Our journey now brings us to worlds of extreme heat, though different in character from the hot Jupiters. These are the lava worlds, rocky planets that orbit so close to their stars that their surfaces are perpetually molten, their crusts flowing like honey, their atmospheres thick with vaporized rock. These are not large gas giants, but Earth-sized worlds or smaller, planets that might once have been habitable if they had formed at greater distances, but instead find themselves in orbital positions where their surfaces reach temperatures hot enough to melt stone. Let us begin with Kepler 10b, one of the first rocky exoplanets ever confirmed. This world orbits a sun-like star approximately 560 light-years away, but it does so at a distance of only about 2 million miles, more than 20 times closer than Mercury orbits our Sun. Its year lasts merely 20 hours. The dayside temperature of Kepler 10b exceeds 2,500 degrees Fahrenheit, hot enough to melt iron. This planet is roughly 1.4 times the diameter of Earth and about 4.6 times its mass, giving it a density that suggests it is made primarily of rock and iron, similar to Earth's composition. The extreme heat means that Kepler 10b cannot retain any atmosphere in the traditional sense. Any gases would be blown away by the intense radiation and stellar wind from its nearby star. Instead, the planet likely has a thin envelope of vaporized rock, silicate vapor that rises from the molten surface, cools slightly at altitude, and then falls back down as rain of liquid rock. This is not a metaphor or artistic license. This is what the physics and chemistry of such extreme conditions predict. 55 Cancri e, located approximately 41 light-years away, offers another window into these molten worlds. This planet is roughly twice Earth's diameter and nearly 8 times its mass. It orbits its star in less than 18 hours, positioned so close that it is tidally locked. Recent observations have revealed something extraordinary about this world. Its dayside temperature varies by more than 2,000 degrees Fahrenheit over time. This dramatic variation suggests that the planet's molten surface might be covered by lava lakes and flows that change in configuration, or that volcanic activity resurfaces portions of the planet, temporarily cooling them before they heat up again. Scientists have proposed that 55 Cancri e might be rich in carbon, potentially enough that, under the extreme pressures in its interior, a portion of that carbon could form diamonds. This has led to the popular description of 55 Cancri e as a diamond planet, though we should be cautious with such characterizations. While thermodynamic models suggest that diamond could be stable in the planet's interior, we have no direct evidence of this. And the planet's surface conditions, temperatures exceeding 4,000 degrees Fahrenheit and a surface of molten rock, would certainly dominate any visitor's experience. K2-141b takes the concept of a lava world to even greater extremes. This planet, discovered by the K2 mission and located approximately 200 light-years away, completes an orbit every 7 hours. Yes, 7 hours for an entire year on this world. The dayside temperature is estimated to exceed 5,000 degrees Fahrenheit, hot enough not just to melt rock, but to vaporize it. Scientists believe that K2-141b has a weather system, but not like anything on Earth. On the permanent day side, rocks vaporize. These vapors are carried by supersonic winds to the night side, where temperatures are cool enough, though still over 3,000 degrees, for the rock vapor to condense into liquid. This liquid rock then flows back toward the day side in literal lava rivers, completing a bizarre cycle analogous to Earth's water cycle, but with molten stone instead of water. Crow 7b, discovered by the French-led Corot mission before Kepler, was one of the first rocky exoplanets found. Located about 500 light-years away, it is approximately 60% larger than Earth and orbits its star every 20 hours. The surface temperature on the day side reaches approximately 4,000 degrees Fahrenheit. What makes Corot 7b particularly interesting is that scientists have attempted to model what its atmosphere might contain. The model suggests that the air, if we can call it that, might contain gaseous rock components, sodium, potassium, silicon monoxide, and even vaporized iron. When this vapor cools on the night side, it likely condenses and falls as rain of liquid rock, or perhaps even as snow of solid minerals. These lava worlds force us to expand our definition of what a planet can be. They blur the line between solid and liquid, between surface and atmosphere. On Earth, we stand on solid ground beneath a gaseous sky. On these worlds, the surface itself flows, and the sky may be made of the same materials as the ground, merely heated to a different state. The existence of these lava worlds also tells us something about planetary migration and system evolution. Many of these planets likely formed farther from their stars, where temperatures were cooler, and then migrated inward over time. Some might be the remnant cores of larger planets that lost their outer layers through evaporation. Others might have been scattered into their current orbits through gravitational interactions with other planets in their systems. As you contemplate these worlds, let yourself drift in imagination over a landscape unlike anything in our solar system. Rivers of molten rock flow across plains of barely solid basalt. The sky glows with the heat of the nearby sun, a bloated disk of searingly bright light. Rock vapor rises in shimmering waves. On the terminator, the boundary between day and night, the temperature gradient is so extreme that rock transitions from vapor to liquid to solid within a relatively short distance. These are young worlds in a sense, constantly renewed by their own melting, never cooling enough to form the kind of stable crust and atmosphere that allows for geological history to be recorded. Let us now journey to one of the most evocative types of planetary systems discovered by Kepler, the circumbinary planets. These are worlds that orbit not one star, but two, binary star systems where the planets experience the rise and set of dual suns. The image is iconic from science fiction, particularly from the scene in Star Wars where Luke Skywalker watches the double sunset on Tatooine. But Kepler and TESS have shown us that such worlds are not merely fictional. They are real, and they challenge our understanding of how planets can form in complex gravitational environments. Binary star systems are common in our galaxy. Roughly half of all sun-like stars exist in binary or multiple star systems, orbiting each other in gravitational embrace. For decades, scientists debated whether planets could form in such systems. The gravitational perturbations from two stars orbiting each other seemed likely to disrupt the process of planet formation, flinging away the dust and gas needed to build worlds. Yet nature, as it so often does, found a way. Kepler 16b was the first confirmed circumbinary planet discovered by the Kepler mission, announced in 2011. Located approximately 200 light-years away in the constellation Cygnus, this world orbits two stars that themselves orbit each other every 41 days. The planet is roughly the size and mass of Saturn and orbits its binary stars every 229 days, about 7.5 months, at a distance comparable to Venus's distance from our Sun. The two stars of the Kepler 16 system are unlike our Sun. One is an orange dwarf star with about 69% of the Sun's mass, while the other is a red dwarf with just 20% of the Sun's mass. They orbit each other at a distance less than the distance between the Sun and Mercury. From the surface of Kepler 16b, if you could somehow stand on this gas giant's cloud tops, you would see two suns of different colors and sizes orbiting each other, rising and setting together, then separated, creating complex patterns of light and shadow across the sky. What makes circumbinary planets particularly remarkable is the precision required to detect them. When a planet transits a single star, it causes a regular, predictable dimming pattern. But when a planet orbits two stars, the stars themselves are eclipsing each other as they orbit, creating a complex pattern of brightness changes. The planet's transit adds another layer of variation. And because the planet's position relative to the two stars changes over time due to their motion, the timing and depth of the planet's transits vary in complicated ways. Disentangling these signals requires sophisticated analysis. Yet Kepler found not just one, but 13 confirmed circumbinary planets during its mission. Kepler 47 is perhaps the most remarkable of these systems. Located approximately 3,000 light-years away, it is the only known multi-planet circumbinary system. 2 planets orbit a pair of stars, one sun-like star and one red dwarf that orbit each other every 7.45 days. The inner planet, Kepler 47b, is roughly 3 times Earth's diameter and orbits the binary every 49 days. The outer planet, Kepler 47c, is approximately 4.5 times Earth's diameter and orbits every approximately 303 days. What makes this system especially intriguing is that Kepler 47c orbits within the habitable zone of its binary stars, the region where temperatures might allow liquid water to exist on a moon orbiting the planet, if such a moon existed. The formation of circumbinary planets presents theoretical challenges. Planets form from disks of gas and dust that surround young stars. In a binary system, the gravitational influence of both stars creates gaps and perturbations in this disk. The region very close to the binary is cleared out by gravitational interactions. Planets can form in the disk beyond a certain distance from the binary, typically a few times the separation between the 2 stars, where the disk becomes stable enough for planetary formation to proceed. Kepler 413b illustrates another fascinating aspect of circumbinary systems. This Neptune-sized planet orbits 2 stars located approximately 2,300 light-years away, but its orbit is tilted at an angle relative to the plane in which the 2 stars orbit each other. Over time, an 11-year cycle, this tilt causes the planet's orbital plane to precess, wobbling like a spinning top. This means that the planet's transits as seen from Earth are not always aligned correctly for us to observe them. The planet appeared in Kepler's data, then disappeared for a time as its orbital precession carried it out of alignment, then reappeared. This discovery demonstrated that some circumbinary planets might go undetected simply because we observe them during phases when their orbits are not favorably aligned. The long-term stability of these systems is another area of active research. Computer simulations show that circumbinary planets need to orbit beyond a certain minimum distance to remain stable, typically at least 2 to 3 times the separation between the binary stars. Closer than this, and the complex gravitational pulls from the 2 stars can destabilize the planet's orbit over time, potentially ejecting it from the system. All the circumbinary planets discovered so far orbit beyond this stability limit, suggesting that closer circumbinary planets either never formed or did not survive. As you let your mind wander through these systems, imagine the experience of living in such a place. The daily cycle of light and darkness would be complex, unlike anything we experience on Earth. Depending on the planet's position in its orbit and the configuration of the binary stars, there might be times when both stars are above the horizon, providing bright daylight. Other times, one star might set while the other remains up, creating a twilight of sorts. The stars' orbital motion around each other would create shifting patterns of illumination, with no 2 days exactly alike in terms of how the sunlight falls. These worlds remind us that planetary systems can exist in configurations that seem precarious to us, yet stable over billions of years. They expand our sense of where planets can form and survive, pushing the boundaries of the possible ever outward. Now we drift toward planets that capture our imagination in a different way, not through their extremes of heat or size, but through their tantalizing hints of familiarity. These are the smaller planets orbiting in the habitable zones of their stars, worlds where temperatures might allow liquid water to exist on their surfaces, where conditions might be suitable for life as we know it. Let us begin with the TRAPPIST-1 system. Though it was not discovered by Kepler or TESS, but rather by the transiting planets and planetesimal small telescope. It represents the kind of system these missions have helped us understand. Located approximately 39 light-years away, TRAPPIST-1 is an ultra-cool red dwarf star, much smaller and dimmer than our Sun. Around this star orbit 7 Earth-sized planets, all packed into orbits closer than Mercury is to our Sun. 3 of these planets, TRAPPIST-1, E, F, and G, orbit within the star's habitable zone. Because the star is so much cooler than our Sun, its habitable zone is much closer in. The planets orbit their star every few days to about 3 weeks. All 7 planets are likely tidally locked, with one side permanently facing the star and the other in eternal darkness. Yet the atmospheres of these planets, if they have substantial atmospheres, might redistribute heat from the day side to the night side, potentially making them more hospitable than we might initially think. Kepler 442b, located 1,100 light-years away, is one of the most potentially Earth-like planets discovered by Kepler. It is about 33% larger than Earth and orbits within its star's habitable zone, completing an orbit every 112 days. Its star is a K-type orange dwarf, cooler and smaller than our Sun, but more stable and long-lived than red dwarfs. Kepler 442b receives about 70% of the light that Earth receives from the Sun, comparable to what Mars receives. If the planet has a substantial atmosphere with greenhouse gases, it could maintain liquid water on its surface. The habitable zone concept itself deserves gentle explanation. This is the range of distances from a star where a rocky planet with an atmosphere could maintain liquid water on its surface. It's not too close where water would boil away and not too far where it would freeze solid. The habitable zone's location depends on the star's temperature and brightness. For our Sun, it extends roughly from Venus's orbit to somewhat beyond Mars. For cooler stars, it's closer in. For hotter stars, farther out. However, being in a habitable zone does not guarantee habitability. Venus orbits within our Sun's habitable zone, yet its surface is hot enough to melt lead due to a runaway greenhouse effect. Mars also orbits near the outer edge of the habitable zone, yet its thin atmosphere and lack of a magnetic field make it inhospitable to life on its surface today. A planet needs not just the right distance from its star, but also the right mass, atmospheric composition, magnetic field, and perhaps other factors we don't yet fully understand. Kepler 62f, located 1,200 light-years away, is another intriguing world. Approximately 40% larger than Earth, it orbits its star every 267 days, receiving less sunlight than Earth does, but potentially warm enough for liquid water if it has the right atmosphere. Scientists have created models suggesting that if Kepler 62f has an atmosphere with abundant carbon dioxide, several times more than Earth's atmosphere, it could maintain temperatures above freezing across much of its surface. TOI 700d, discovered by TESS, represents the kind of nearby, bright star targets that TESS was designed to find. Located 100 light-years away, relatively close in astronomical terms, this planet is approximately 20% larger than Earth and orbits within its star's habitable zone every 37 days. Its star is a red dwarf, cooler and dimmer than our Sun. TOI 700d receives about 86% of the energy from its star that Earth received from the Sun. Follow-up observations with other telescopes are planned to search for an atmosphere on this world. The search for Earth-like planets faces several challenges. Smaller planets produce smaller signals in the data, less dimming when they transit, smaller wobbles in their star's motions. Earth-sized planets in year-long orbits around Sun-like stars are at the edge of what Kepler could reliably detect. The mission needed to observe at least 3 transits to confirm a planet, which for a planet in a 1-year orbit meant at least 3 years of observations. By the time Kepler's primary mission ended, it had observed enough to detect such planets, though confirming and characterizing them continues to require painstaking analysis. Another challenge is that most of the potentially habitable planets discovered so far orbit red dwarf stars, not sun-like stars. Red dwarfs are the most common type of star in the galaxy, comprising about 70% of all stars. They're also smaller and dimmer, which makes planet detection easier. But red dwarfs have their own challenges for habitability. Many produce powerful flares, sudden bursts of radiation that could strip away a planet's atmosphere over time. Planets in their habitable zones orbit very close due to the star's dimness, which subjects them to stronger tidal forces and more intense stellar wind. Yet some scientists argue that red dwarf planets might be our best bet for finding life elsewhere. These stars live for trillions of years, compared to the Sun's 10 billion-year lifespan. That provides immense timescales for life to develop and evolve. The planets in their habitable zones, while close to their stars, might be protected by strong magnetic fields or thick atmospheres. As you contemplate these worlds, let your mind rest on the profound questions they raise. We do not yet know if any of these planets have the conditions necessary for life. We have not detected atmospheres on most of them, let alone water vapor, oxygen, or other biosignatures. But they represent possibilities, worlds that might be homes to life, places where the universe might have experimented with biology in ways similar to or vastly different from Earth. These temperate worlds remind us why we search the skies. Among the thousands of planets discovered, there might be places where water pools and lakes, where atmospheres cycle gases through processes both geological and biological, where the conditions for life, that most remarkable of the universe's phenomena, might exist. For now, they remain mysterious, distant points of light that dim their stars by tiny fractions. But they are real places waiting to be explored. Let us turn our attention now to a different kind of strangeness, not in the planets themselves necessarily, but in the paths they trace through space. In our solar system, most planets follow nearly circular orbits. Earth's orbit is almost a perfect circle. Even Mercury, with the most eccentric orbit of the major planets, traces an ellipse that is still relatively modest in its elongation. But many exoplanets discovered by Kepler and TESS follow highly eccentric orbits, elongated ellipses that bring them close to their stars at some points and carry them far away at others. An orbit's eccentricity is measured on a scale from 0 to 1. 0 represents a perfect circle, while values closer to 1 represent increasingly elongated ellipses. Earth's orbital eccentricity is just 0.0167. Mercury's is 0.2056. But some exoplanets have eccentricities of 0.7, 0.8, or even higher. Orbits so elongated that the planet's distance from its star varies by factors of 3, 4, or more over the course of a year. HD 80606b, though discovered before the Kepler mission, represents one of the most extreme cases. This planet, approximately 4 times Jupiter's mass, orbits a sun-like star 190 light-years away. Its orbital eccentricity is approximately 0.934, among the highest known for any planet. At its closest approach to its star, called perihelion, HD 80606, B comes within about 4.5 million miles of its star, closer than any planet in our solar system approaches the Sun. At its farthest point, aphelion, it travels out to approximately 85 million miles, roughly Earth's distance from our Sun. The consequences of such an eccentric orbit are dramatic. When HD 80606b makes its close approach to its star every 111 days, its temperature skyrockets. Within just 6 hours of perihelion passage, the planet's dayside temperature increases from about 900 degrees Fahrenheit to over 2,000 degrees Fahrenheit. This is not a gradual seasonal change, but a violent thermal shock that the planet experiences regularly. Powerful winds likely race through the planet's atmosphere as it tries to redistribute this sudden influx of heat. Scientists believe that HD 80606b's eccentric orbit resulted from gravitational interactions with other planets or perhaps with a stellar companion. In multi-planet systems, gravitational encounters between planets can pump up orbital eccentricity, sometimes dramatically. This is thought to be one mechanism for creating hot Jupiters. A planet on an eccentric orbit gradually spirals inward due to tidal interactions with its star, with the orbit becoming more circular as the planet settles into a close, stable orbit. Kepler discovered hundreds of planets on eccentric orbits, though most are less extreme than HD 80606b. Kepler 432b, for instance, has an eccentricity of about 0.51. This planet, roughly 6 times Jupiter's mass, orbits every 52 days, with its distance from its star varying by roughly a factor of 2. At perihelion, the planet experiences intense heating. At aphelion, it cools significantly. This creates a rhythm of extreme seasons compressed into a 52-day cycle. Not seasons caused by axial tilt as on Earth, but purely from the changing distance to the star. For smaller, potentially rocky planets, eccentric orbits raise interesting questions about habitability. A planet might spend part of its orbit in the habitable zone and part outside it. If the eccentricity is modest, this might create extreme seasons but still allow for liquid water during parts of the year. If the eccentricity is high, the planet might freeze solid at aphelion and become scorching hot at perihelion, perhaps maintaining liquid water only during the brief periods when it passes through the habitable zone. Kepler 432b's parent star is itself evolving, having exhausted the hydrogen in its core and expanded into a red giant face. This adds another dimension to the planet's story. As the star has expanded, it has increased in brightness, likely having already engulfed and destroyed any inner planets that once orbited closer. Kepler 432b itself is destined for eventual destruction. In about 200 million years, the expanding star will engulf the planet during one of its close perihelion passages. The study of eccentric orbits has revealed that planetary systems can be much more dynamically active than we once thought. In our solar system, the planets have settled into stable, nearly circular orbits that they have maintained for billions of years. But many planetary systems appear to have undergone significant gravitational upheaval. Close encounters between planets, migration of giant planets through the system, perhaps even ejection of planets into interstellar space. Computer simulations of planetary system formation often show chaotic early periods. Multiple gas giant planets form, and their gravitational interactions become unstable. Planets swing by each other in close encounters, exchanging orbital energy and angular momentum. Some planets are thrown onto highly eccentric orbits. Others might be ejected from the system entirely, becoming rogue planets wandering through interstellar space. Eventually, the system settles into a stable configuration, but one that may look very different from the original arrangement. P2b provides another example. This planet, approximately 8 times Jupiter's mass, massive enough that some scientists debate whether it should be classified as a planet or a brown dwarf, has an orbital eccentricity of about 0.517. Its orbit takes it from about 5 million miles from its star at perihelion to about 15 million miles at aphelion. The planet's shape itself is likely distorted by tidal forces, stretched into an elongated form at perihelion when tidal forces are strongest, then relaxing to a more spherical shape at aphelion. As you drift through these thoughts, imagine the experience of existing in a system with such eccentric orbits. The star grows and shrinks in the sky over the course of weeks or months, not in a gentle cycle, but dramatically. The amount of light and heat received varies by factors of 10 or more. For any moons orbiting such planets, the gravitational stresses would vary wildly, potentially driving intense tidal heating that might melt their interiors and create volcanic activity. These eccentric orbits remind us that planetary systems are not static, unchanging arrangements, but dynamic environments shaped by gravity's intricate dance. The orbits we observe today are snapshots of systems still evolving, still responding to the gravitational influences that shaped them billions of years ago and continue to shape them today. Our journey now takes us to the planets that move faster than any others, the ultra-short period planets. These are worlds whose years are measured not in days, but in hours. They race around their stars at speeds so great that they complete multiple orbits in a single Earth day. These planets push the boundaries of what seems physically possible, existing on the edge between a stable orbit and eventual destruction. An ultra-short period planet is typically defined as one with an orbital period less than one Earth day, 24 hours. To orbit so quickly, these planets must be extraordinarily close to their stars, closer even than the hot Jupiters we explored earlier. And because gravity tears apart anything too large that orbits too close, ultra-short period planets are always small, typically Earth-sized or smaller. They are rocky worlds stripped of any atmosphere they might once have had, their surfaces directly exposed to intense stellar radiation. K2-137b holds the record for the shortest known orbital period of any confirmed planet. Located approximately 180 light-years away, this planet completes one orbit in just 4.3 hours. To accomplish this, it orbits at a distance of only about 1.5 million miles from its star, less than 1% of Earth's distance from the Sun, and closer than any planet in our solar system orbits. The planet is slightly smaller than Earth, with a radius about 77% that of Earth's. The surface conditions on K2-137b are extreme. The dayside temperature is estimated to exceed 4,000 degrees Fahrenheit. The planet is almost certainly tidally locked, with one hemisphere perpetually facing its star. At such close range, the tidal forces are enormous, potentially flexing and heating the planet's interior through friction, similar to the tidal heating that drives volcanic activity on Jupiter's moon Io, though far more intense. Epoch 2288139118b, discovered during Kepler's K2 mission, has an orbital period of 4.34 hours, nearly identical to K2-137b. This planet is about 1.4 times Earth's radius and is remarkably dense, suggesting a composition rich in iron. Scientists speculate that this planet might be the exposed iron core of what was once a much larger planet, perhaps a gas giant whose outer layers were stripped away by the intense radiation and tidal forces so close to its star. The process that creates ultra-short period planets is not fully understood. They may be the remnants of larger planets that migrated inward and lost their outer layers. Or they might be planets that formed close to their stars, but at slightly greater distances, then spiraled inward over time. Another possibility is that they were scattered into their current orbits by gravitational encounters with other planets, arriving on highly eccentric orbits that tidal forces gradually circularized very close to the star. These planets cannot survive indefinitely in their current positions. They are losing mass through evaporation, their surfaces being stripped away by the intense stellar radiation. They are also being pulled gradually closer to their stars by tidal interactions. Eventually, perhaps in millions or tens of millions of years, they will spiral into their stars and be destroyed. We may be observing these planets during the final stages of their existence, cosmic mayflies racing toward their inevitable end. Kepler 78b, located about 700 light-years away, provides another example. This planet has an orbital period of just 8.5 hours and a radius only about 20% larger than Earth's. Intriguingly, its density is very similar to Earth's, suggesting a similar composition of rock and iron. Yet the planet's surface temperature exceeds 3,000 degrees Fahrenheit, and it has no atmosphere. It is sometimes described as Earth's evil twin, similar in size and composition, but in a completely inhospitable location. The discovery of these ultra-short period planets was unexpected. Before Kepler, theoretical models suggested that planets could not survive at such close distances. Tidal forces would rip them apart, or they would spiral into their stars too quickly. Yet Kepler found dozens of these planets, forcing theorists to revise their models of what conditions planets could endure. 55 Cancri E, which we encountered earlier as a lava world, has an orbital period of about 17.7 hours, placing it in the ultra-short period category, though not quite at the extreme end. This planet's variations in temperature and the possible presence of a thin, unstable atmosphere or vaporized surface materials make it a subject of intense study for understanding conditions at these extreme distances. One fascinating aspect of ultra-short period planets is what they can tell us about planetary interiors. At such close distances, precise measurements of the planet's orbit can reveal subtle effects of the star's tidal forces on the planet's shape and structure. If the planet is somewhat fluid or has a molten interior, it will deform more under tidal stress than if it is solid throughout. These tiny deformations affect the planet's gravitational field, which in turn slightly alters its orbit in detectable ways. From such measurements, scientists can infer details about the planet's internal structure, whether it has a molten core, how rigid its mantle is, and so on. These worlds also serve as natural laboratories for studying extreme physics. The temperatures and radiation levels they experience exceed anything we can easily reproduce in laboratories. Observing how materials behave under such conditions, how rock vaporizes, how tidal forces deform planetary bodies, how magnetic fields, if any, interact with intense stellar winds, extends our understanding of matter and energy. As you contemplate these speed demon worlds, let your thoughts drift gently through the physics of their existence. Every few hours, they complete a full orbit, sunrise, noon, sunset, and midnight in the span of time it takes to watch a movie. Yet for these tidally locked worlds, there is no real cycle of day and night, only the eternal fierce blaze on one side and the perpetual darkness on the other. They are places of extremes, existing at the edge of possibility, reminders that the universe explores every niche where matter can exist, even if only temporarily. Our journey takes a somber turn now, toward planets that orbit not living stars, but dead ones. These are worlds circling white dwarfs, the dense, cooling embers left behind after sun-like stars exhaust their nuclear fuel. Some planets even orbit neutron stars and pulsars, the collapsed cores of massive stars that exploded as supernovae. These planets exist in twilight realms, illuminated by the fading light of stars that have already died, survivors of cataclysms that should have destroyed them. White dwarfs are what become of stars like our Sun after they exhaust their hydrogen fuel. The star swells into a red giant, potentially engulfing its inner planets, then sheds its outer layers into space, leaving behind a hot, dense core about the size of Earth, but containing roughly half the Sun's mass. This core cools over billions of years, gradually fading from white-hot to yellow to red, and eventually to black, though the universe is not yet old enough for any white dwarf to have cooled to complete darkness. WD 1856 plus 534b, discovered by TESS in 2020, is a remarkable world. This Jupiter-sized planet orbits a white dwarf star located about 80 light-years away, completing an orbit every 1.4 days. The planet passes directly in front of the white dwarf as seen from Earth, blocking about half of the star's light during each transit. An enormous signal because the white dwarf is so small, only about 40% larger in diameter than Earth, despite being far more massive. The mystery of WD 1856 plus 534b is how it survived. When this white dwarf's progenitor star became a red giant, it would have expanded to perhaps 100 times its current size, likely reaching out to at least the current orbital distance of Earth, possibly farther. Any planet originally at the location where WD 1856 plus 534b now orbits would have been engulfed and destroyed. So this planet must have formed much farther out and then migrated inward after the star shed its outer layers and became a white dwarf. The migration mechanism might involve gravitational interactions with other planets in the system. During the red giant phase, planets are thought to move outward as the star loses mass, but their relative positions and orbital dynamics can become unstable. Gravitational encounters between planets could have flung WD 1856 plus 534b inward, where tidal interactions with a white dwarf then circularized its orbit. Pulsar planets present an even stranger scenario. Pulsars are rapidly rotating neutron stars, objects about 10 miles in diameter but more massive than the Sun, spinning many times per second and beaming radiation from their magnetic poles like cosmic lighthouses. The first exoplanets ever discovered, back in 1992, were 3 planets orbiting the pulsar PSRB 1257 plus 12. These pulsar planets were not detected through transits or wobbles, but through tiny variations in the pulsar's radio signals. Pulsars emit radio waves with extraordinary regularity, more precise than any human-made clock. But when planets orbit the pulsar, their gravitational pull causes the pulsar to wobble slightly. This wobble shifts the arrival times of the radio pulses by microseconds, variations small enough that they were initially thought impossible to detect, yet precise enough that they revealed not just the presence of planets, but detailed information about their masses and orbits. The 3 planets of PSRB 1257 plus 12 orbit at distances of roughly 0.2, 0.4, and 0.5 astronomical units from the pulsar. Their masses range from roughly twice Earth's mass to 4 times Earth's mass. They are probably rocky worlds, cold and dark, illuminated only by the faint glow of the pulsar's radiation and perhaps by the faint stars in the background. The question of how these planets formed is profound. Neutron stars are created in supernova explosions, violent events that blast away any planets originally orbiting the star. The temperatures and radiation levels during and after supernova are extreme enough to vaporize rocky planets. So the pulsar planets likely formed after the supernova, condensing from the debris disk left over from the explosion or from material pulled off a companion star. They are second-generation planets, worlds born from the ashes of a star's death. Some scientists have proposed that certain white dwarfs show signs of accreting rocky material. Essentially, the remains of asteroids or planets that were torn apart by the white dwarf's gravity and fell onto its surface. The chemical signatures of elements like calcium, magnesium, and iron in the white dwarf's atmosphere, which should have sunk to its core due to the intense gravity, suggest ongoing accretion of rocky debris. This implies that these white dwarfs have or recently had asteroid belts or broken up planets in their vicinity. These systems offer a glimpse into what might happen to our own solar system billions of years in the future. When the Sun becomes a red giant in approximately 5 billion years, it will expand and likely engulf Mercury and Venus. Earth's fate is uncertain. It might be engulfed, or it might survive in a wider orbit, heated to uninhabitability. Mars, Jupiter, Saturn, and the outer planets will likely survive, though their orbits will expand as the Sun loses mass. After the Sun becomes a white dwarf, these planets will orbit in a cold, dark system illuminated only by the white dwarf's dim glow and the light of distant stars. The survival of planets around evolved stars tells us about the resilience of planetary systems. Stars undergo dramatic changes, swelling to hundreds of times their original size, shedding large fractions of their mass, potentially exploding. Yet planets can survive these transformations, adapting to wildly different conditions. A planet that formed in a bright, warm environment might end its existence orbiting a cooling ember, its surface frozen, its atmosphere, if any, collapsed into ice on its surface. As you let these thoughts settle, imagine the profound loneliness of a planet orbiting a white dwarf. The star provides little warmth, just a faint glow. The sky is dark, filled with the unchanging stars of the galaxy. Billions of years pass, and nothing changes except the slow, gradual cooling of the star. These are worlds in perpetual twilight, silent monuments to stellar death, yet also testaments to the endurance of matter across cosmic time. We have journeyed together through a cosmos far richer and stranger than anyone imagined before the Kepler and TESS missions began their patient watch of the stars. From worlds ablaze with heat to planets with two suns, from Earth-sized rocks racing around their stars in hours to survivors orbiting dead stars in eternal twilight. We have seen that nature's creativity in constructing planets exceeds anything we might have predicted. Let us reflect gently on what these discoveries mean. Before 1995, we knew only one planetary system, our own. We had theories about how planets formed, based entirely on studying the Sun's family of worlds. We wondered whether planets were common or rare. We debated whether our solar system's architecture, small rocky planets near the Sun, gas giants farther out, represented the typical configuration, or if it was one possibility among many. Now we know. Planets are common, perhaps outnumbering stars. Planetary systems display enormous diversity. Hot Jupiters orbit closer to their stars than we thought possible. Super-Earths and mini-Neptunes, types absent from our solar system, may be the most common planets in the galaxy. Planets orbit binary stars, exist on highly eccentric orbits, race around their stars in hours, and survive around dead stars. The universe has shown us that nearly every configuration allowed by physics actually exists somewhere. Kepler's legacy extends beyond the individual planets it discovered. The mission provided statistical insight into planetary occurrence rates. By watching 150,000 stars for years, Kepler gave us a census of planets. Scientists can now estimate that roughly 30 to 50% of Sun-like stars host planets in their habitable zones. Extrapolating to the hundreds of billions of stars in our galaxy, this suggests billions of potentially habitable worlds exist in the Milky Way alone. TESS continues this work, focusing on brighter, nearer stars that are better targets for detailed follow-up observations. The planets TESS discovers can be studied by other telescopes, measuring their masses with ground-based instruments, analyzing their atmospheres with space telescopes. This is the next frontier, moving beyond merely detecting exoplanets to actually characterizing them, understanding what they're made of, whether they have atmospheres, and what those atmospheres contain. The James Webb Space Telescope, launched in 2021, has begun observing exoplanet atmospheres in unprecedented detail, detecting molecules like water vapor, carbon dioxide, and sulfur dioxide. Future missions are planned specifically to search for biosignatures, chemical signs of life, such as oxygen and methane in atmospheres where they wouldn't persist without biological processes to replenish them. We are moving from discovery to understanding, from cataloging planets to potentially finding life beyond Earth. Yet even as technology advances, the fundamental challenge remains. Interstellar distances are vast beyond human comprehension. The nearest star system, Alpha Centauri, is about 4 light-years away. At current spacecraft speeds, it would take tens of thousands of years to reach even this closest neighbor. The planets discovered by Kepler and TESS are dozens, hundreds, or thousands of light years distant. We cannot visit them with current technology. We cannot send probes that would return data within human lifetimes. We can only observe from afar, using light that left those worlds years or centuries ago, and infer what conditions might be like. This limitation makes the discoveries all the more remarkable. From Earth's orbit or surface, using telescopes and careful analysis, humanity has detected and characterized thousands of worlds we can never touch. We have learned their sizes, masses, temperatures, and orbits. We have begun to understand their atmospheres and surfaces. We have done this by measuring dimming of starlight by tiny fractions, by detecting wobbles in stellar motion measured in meters per second, by analyzing subtle shifts in the color of light. The strange planets of Kepler and TESS also inspire philosophical reflection. We live on a world of moderate temperature, orbiting a single sun at a distance where water can be liquid, where years last a comfortable length, where our planet has had billions of years of relative stability, allowing life to evolve in complexity. We now know that this is not the typical planetary experience. Most planets endure extreme conditions, scorching heat or frozen darkness, intense radiation, wildly eccentric orbits, tidal locking. Earth's temperance may be unusual, perhaps even rare. This realization brings both humility and wonder. Humility because we see that our home is not the template for all worlds, but perhaps an outlier, lucky in its circumstances. Wonder because the universe has created such diversity, exploring every possibility, filling every niche where matter can persist. And perhaps, hidden among those billions of worlds, are other temperate places where life has emerged, where other forms of awareness contemplate their skies and wonder, as we do, what lies beyond. As you drift towards sleep, let your mind wander among these distant worlds. Imagine the double sunset on a circumbinary planet, the colors of two stars blending in the sky. Picture the silent, frozen surface of a planet orbiting a white dwarf, lit by dim, fading light. Feel the rush of a world racing around its star in hours, perpetually daylit on one side, dark on the other. See in your minds a river of molten rock flowing across a lava world. Hear the glass rain falling sideways on a hot Jupiter. Sense the profound strangeness of planets so different from our own, yet bound by the same physical laws. The search continues. TESS is still operating, scanning the sky for new worlds. Ground-based telescopes follow up on the most interesting candidates. New missions are being planned. With each passing year, we refine our understanding, discover new types of worlds, probe deeper into the question of whether we are alone. The strange planets found by Kepler and TESS are not endpoints, but beginnings. First glimpses into the true diversity of worlds that exist in our galaxy. Sleep now and dream of distant suns and alien skies, of worlds that orbit in configurations we're only beginning to understand, of the vast cosmic ocean of planets waiting to be explored. We have seen strange worlds, and they have changed forever how we understand our place in the cosmos. The universe is larger, more diverse, and more wondrous than we knew. And somewhere among those countless worlds, perhaps, are places even stranger than we have yet imagined, waiting for future generations to discover them, one patient observation at a time.